The part of calculus usually studied first is called differential calculus. It is so named because the difference between the x and y values of 2 points on a function can tell us a lot about what the function is doing at one of those points. What kinds of things can we tell from this, and why do we care? Let's begin with the familiar function graphed here, f of x equals x squared. Our goal is to find out a few things about f at the point 1, 1. To start with, we'll just take a visual look at the graph to answer the following questions. Remember, we read graphs left to right, except when we consider end behavior, which is not part of this presentation. At the point 1, 1, is f increasing or decreasing, and how do you know? And is f concave up or curving upward, or is it concave down, curving downward, and how do you know? Pause the video and answer the questions. These seemingly simple questions might have been unexpectedly difficult to answer concisely. But suppose that the part of the graph near 1, 1 represented our company's sales over a period of time. Not only are sales increasing, because the y value of f is increasing as x increases, but they seem to be increasing faster as time goes by. The change in y is greater for a given time interval after x equals 1 than for the same time interval before x equals 1. Here's another question about the graph. At what point, xy, does f reach its minimum value? And how do you know? Once again, pause the video and answer the question. While you can easily answer this question based on just looking at the y value of the graph, consider another way to think about this. At f's minimum point, 0, 0, we can see that the graph is changing from decreasing to the left of 0, 0 and increasing to the right of 0, 0. In fact, right at the exact point 0, 0, the graph is neither increasing nor decreasing. So let's pause for a second and think about how we answered these questions. In each case, we considered whether the graph was increasing or decreasing at a single point. Visually, this is easy to do. But we won't always have a graph to look at, and we won't always be dealing with any particular function. We might want to develop general rules and procedures that can apply to all functions. So let's look at this a little more analytically. Let's go back to a simple function, the straight line. When we think about a line, we can visualize a line whose y value increases from left to right, and a different line whose y value decreases from left to right. We can even think of a line whose y value neither increases nor decreases. So what 10-letter word describes a line whose y value neither increases nor decreases? What is the characteristic of a line that tells us whether it's increasing, decreasing, or neither? And using that characteristic, how can we tell if a line's y value is increasing? How can we tell if its y value is decreasing? And how could we tell if its y value is neither increasing nor decreasing? Once again, pause the video and answer the questions. Now let's connect these lines to analyzing our function f. How does a straight line help us to understand what's happening on a curved function? When you looked at the graph at the points 0, 0 and 1, 1, you weren't really looking only at those single points in isolation. You decided that f was increasing at 1, 1 because you saw a smaller y value to the left of the point and a larger y value to the right. Smaller to larger is increasing. Well, consider what would happen if we drew a line through the points 1, 1 and another point just to the right of 1, 1. Is the slope of this line positive or negative? And what does your answer tell you about the behavior of f right at 1, 1? Pause the video and answer the question. Here is arguably the most important thing to remember about differential calculus. The piece of a function graph between 2 points that are close together can be approximated by a straight line. And the closer together the 2 points are, the better the line approximates the function's rate of change at either of these points. Now this statement has some conditions attached to it, but we'll save that for another day. Now what do we mean by rate of change? It's the amount that the y value changes when the x value changes by a small amount. You can think about it as y value units per x value unit, with the word per telling us that this is a rate. For example, if the y value measures an object's position in meters from some home position, and the x value measures time, then an object whose position, its y value, changes by delta s meters in a time period, its x value of delta t seconds, has a velocity of delta s over delta t meters per second. Therefore, an object's velocity is the rate of change of its position. If delta s equals 6 meters and delta t equals 2 seconds, then the object's position is changing at the rate of 6 meters per 2 seconds, or 3 meters per second. Now, if this object has a constant rate of change, let's say 3 meters per second, then we know that for any time frame of 1 second, it will move by 3 meters. In fact, it will move 3 meters in 1 second, 30 meters in 10 seconds, 21 meters in 7 seconds, etc. Furthermore, it doesn't matter whether we are measuring this velocity near t equals 0 or near t equals 1,000,000 seconds. The graph of its position versus time is a straight line for all values of t, and its rate of change is identical to its constant slope. However, if the object's position is given by a curved graph instead of a straight line, like f of x equals x squared, then this rate of change of the function's y value is different at every point on the graph. This is what got Isaac Newton thinking about how to mathematically describe the motion of a falling object, like an apple. If a falling object is accelerating, meaning its velocity is always increasing, how can we determine its exact instantaneous velocity at a single point in time, and not its average velocity between 2 points in time, no matter how close those points are together? The answer to this question gives us the concept of the tangent line, a line that touches the curve at exactly one single point in a small section of the curve. The slope of this tangent line, shown in red here, matches the rate of change of the curve at the single point of tangency P. And those simple Algebra 1 methods we used to determine the slope of a line given 2 points, P and Q, will extend to find a formula to calculate the instantaneous rate of change of a function, which is the slope of the tangent line at one single point. This formula, derived from f, is called the derivative of f. The derivative is the tool we will use to analyze functions, and it is based on reducing the tiny difference between 2 points on the curve to one single point, thus differential calculus.